Hello, physics fans and sports fans. So we're going to look at an interesting topic, the sweet spot. You might have heard of that. And in baseball, they talk about hitting the sweet spot of the bat. And there's actually some physics to that. So reality or myth, we're going to find out. Let's let the physics decide. We're going to be using angular momentum, and this is an interesting rotation topic. So starting out here, I have some kind of crude animations showing an experiment you can try for yourself. So just read what this says, try what this says, a little experiment, and you can actually see it pretty well. You want to do a sharp strike, and the strike is representing a baseball hitting a bat, and then the end of the ruler resting on the eraser is kind of like the person holding the bat. And what you'll find is that that end will sometimes move one way or the other. So you strike over here and then look carefully, observe where the ruler is sitting on the eraser. And then here are a couple of questions. There is a place, and you might try this just by trial and error, change where you hit the ruler. So are you hitting the ruler near the end, or are you hitting the ruler near the center? There is one spot, and that's the sweet spot, also called the center of percussion, which is a scientific term for it. And what would that do to the motion of the end of the ruler? What does it have to do with hitting a baseball? Why do they call it the sweet spot? I have some animations that might be easier to see, and this will show what should happen. So now let's imagine a more idealized situation. Suppose the bat is floating in space. So I have a baseball bat just floating in space. And then here comes a ball and hits the bat. So in this animation, we're going to see two balls hit two identical bats with different results. So why the different results? Let's watch it one more time. And you're going to notice, if you look closely, you'll see that the balls hit in a different spot. And neither one of these is the so-called sweet spot. Why is the bat or rod on the left side spinning faster? Well, if you think about it, the ball hit nearer the end, it has more torque. And that caused it to rotate faster. If the balls hit equally, the distance that the bats travel would be the same. They would move off at the same speed. It's kind of interesting. So it's like a regular collision, so to speak. But not only is the bat set into motion by the impact of the ball, the bat is set spinning by the ball. And the spinning part is based on torque, angular impulse, you can also say. If there's more torque, there's more angular impulse. Suppose you're trying to hold the bat. So here I just put a hand in my animation. Watch what happens if you're trying to hold it and the ball hits the bat. Then that end of the bat that you're holding is going to move either in the same direction as the ball or the opposite direction of the ball. So I'll do it one more time. Watch what happens. If you needed to, you could rewind the video. Those are pretty decent animations, kind of illustrating what happens. But now, let's suppose you hit in the sweet spot. So the sweet spot would be something in between those other two cases where the rod is going to be spinning just right such that the end you're holding doesn't move instantaneously. And that means that there's been just the right torque, just the right angular impulse to cause the rod to spin at a certain rate such that the end in your hand does not move at that instant. So that's the concept of the sweet spot. We're going to do a problem here in just a minute. I have another illustration of a sweet spot type situation. Suppose I had a disc. Imagine, say, a disc floating on an air hockey table, and you pulled on it. Well, that's going to cause the disc to move, but it's also going to cause the disc to start spinning. Let's watch again. Notice I had kind of one side of the disc touching a little line, and watch that carefully. So look carefully at this spot right here. the blue line on the disk while we run our animation. Notice what my little line said. Not again. So if I pull the disk at the edge of the disk, it starts spinning rapidly. No matter how much force I apply, I'm always going to send that line flying. So let's see what happens here. Suppose I pull on the disk the same amount as before, but now I'm closer to the center of the disk. What do you think is going to happen to the spinning of the disk? Did you say less rapidly? Let's see. Oh yeah, now that's going to cause my little line to move forward with the disk. Let's watch it one more time. Again, focus on where the blue line on the spinning disk connects to the solid line at the top of the disk. Oh yeah, that would kind of drag it forward. But then if I use the so-called sweet spot and I apply a force, this happens. Notice it looks like my wheel is spinning on an imaginary surface. My little line says, phew, he didn't get wiped out that time. Suppose I repeat, and now I pull harder on the same spot. And this is kind of an interesting thing. You could pull as hard as you want at that point, with as much force as you want, and the result would be the same. It would continue to have this effect where that side of the disk, the top side of the disk, doesn't move, and then it would appear to roll even though it's not touching anything. And it would be moving faster if you applied more force. It would be spinning faster, but that combination would occur. Now, let's look at an example problem. So here is an example problem based on the animation you just looked at. And I have this written out, and we're going to look at a little bit at a time. So let's think about the physics of the situation we just saw animated. So suppose a force acts on a disk. The disk is free to move with no friction and no other forces. We're just going to ignore all other forces. It could be a disk floating in space. Or you could imagine, if you wanted to actually try and do this, you can imagine, say, a hockey puck on an air hockey table, and you're just striking it. So if I hit it at just the right spot, it's going to look like it's rolling along an invisible surface. And if you think about what we saw in the video, if you hit it at just the right spot, this bottom part of the wheel or disc would instantaneously not move. So if I apply a force in just the right place, instantaneously the bottom of the disc would not move at all at that instant. So let's look at how we solve a problem like that. What we're going to solve for is what is the value of y, or where on the disk, what distance y from the center of mass would I need to strike the disk. Whenever you're looking at a complex problem like this and you're like, oh boy, what in the world do I do with this? Always start with something basic. So this is an impact. We might think, an impulse of some sort causes a change in momentum. Well, you know what? That's still true. It doesn't matter if it rotates. So whatever force is applied, whatever amount of time it acts, that's going to govern the change in momentum of the disk. So we could say, all right, well, the integral of force and time, that would be the impulse. That should be equal to the mass m of the disk times the velocity of the disk. So the speed or velocity of the disk would be equal to the impulse divided by the mass. And that's true no matter what happens. You could hit it at any value of y. It's just regular old physics. You don't even have to think about the rotation part. But we are thinking about the rotation part. So we can write the same sort of equation for rotation. The net angular impulse A is equal to the change in angular momentum, that's L. So sigma A equals delta L is the rotational version of the same concept. And if we write that out, it looks very similar, but now we've got integral of torque and time, and instead of mv, we have I omega, rotational inertia times the angular velocity. Notice in my torque equation, I have over here y. I've got F times y. That would give me the torque that I am talking about for this problem, right? And then omega could be solved for, and it would be the torque divided by the rotational inertia. Actually, the torque multiplied by the time, basically the angular impulse divided by the rotational inertia, which relates to the torque, but it's like impulse with torque. So notice what happened there. I factored out the y in my formula. I'll try and point that out to you. So right here, I factored out the y, and that's because y would be a particular value. We're going to assume that that doesn't change during the force, the application of the force. All right. Well, okay, so, and that would be independent of what happens in the translation. So whatever's going on with the forward motion of the disk, the spinning of the disk is solely related to that. So one important point to be made here is that when we have this sort of situation, we basically can just do the two things separately. There's the translation world. Everything is what you would expect it to be. It doesn't matter that the force is not at the center of the disk. And then we have the rotation world, and that all works as expected. Although, watch out, you do need to use center of mass. We need to analyze the torque about the center of mass and the rotational inertia about the center of mass. This is an object that doesn't have an axle. There is no defined axis. So kind of a catch there is we want to base our solution on imagining it to spin around the center of mass. And then we can look at the special case. Well, what's special about the sweet spot is the way it would spin versus the way it moves forward. So the special case is let V equal R omega. There's a formula you've seen before. An object rolling on a surface, the speed of that object would be equal to R times its angular speed. So we're imagining that to be the case here, and there is no surface. But if we hit it in just the right place, that should happen. So we're going to use that like a condition, okay? In the condition that this is true, what is the value of y? What have I done here? What I've done here is I have taken the equations that were already set up, and I've highlighted them here. So the little dashed line there, the rotation impulse equals change in angular momentum. And then in the blue rectangles, impulse equals change in momentum, both of which, by the way, we're assuming it started at rest. It was not spinning initially. It was not moving initially. So the change in angular momentum is the final angular momentum, and the change in momentum is the final momentum. But notice those two equations, I could divide one by the other, and if I divide one by the other, a whole lot cancels. The integral disappears. That's kind of cool. So sometimes we're not real happy about having to do these strange integrals. Well, hey, I just got rid of both of them. I just divided, so they cancel. And then that gives me this other stuff remaining. Y is equal to 1/2 mr squared omega divided by mv. And then notice the mass is going to cancel. And I also can do one more thing. So V, we said we had a condition. We were going to let it be equal to R omega. And if I do that, then omega cancels and one of the R's cancels, and then I'm left with the sweet spot. So in this particular situation, this is not true for every object that might go spinning, but this would be true for a disk. That if you hit a disk along a line that's half the way from the center to the edge of the disk, i.e. y equals r over 2, half the radius, the disk would start spinning at a rate such that v equals r omega, no matter how hard or how soft you hit it. And that's an example of finding a sweet spot. The sweet spot of the bat I'll leave that one to you. You can figure it out. You can probably look it up, find it somewhere. I hope you enjoyed this topic.